Hey guys, this is going to be your notes for 3.5. This will wrap up chapter 3. This is going to consist basically of a lot of word problems. And so I'm going into today's notes assuming that you all are by now pretty darn good at solving an exponential and a logarithmic equation. So hopefully you've had quite a bit of practice on doing those things. So let's get started. These are mostly word problems. As you can see, I have used a lot of color in these notes to hopefully try to help you be able to pull information out of a problem and know how to get that information into an equation. So let's take a look at the equations that we're going to be using today. There are 5 of them, and they do kind of look intimidating, but let me start out by saying this. The first 2, I expect you to know, be able to build an equation on your own and be good at solving it. Those are the first 2. The last 3 are used in higher levels of math. So all I need you to be able to do from a pre-cal standpoint is if you're given one of these 3 models, if you're given one of these 3 functions, I just need you to be able to plug numbers into it. Just plug and chug, okay? And so the last 3 are a little more complicated. I will say that this logistic growth model, this one's kind of cool. We use it quite a bit in Calc 2. So if you are a sophomore in pre-cal and you're thinking that Calc 2 might be your final math class here at FC, you will definitely see this function again. But for now, for us in pre-cal, I just need you to be good at the top 2. And here's the thing, exponential growth and exponential decay equations are the same equation. And you have had experience with this equation both in pre-cal and I think in algebra 2. It's just your PERT equation. That's all it is. P(e) to the r times t, PERT equation. Now, in these notes, it has different letters. Instead of a P, they're using an A. Big deal. Still using an E. Instead of R, they're using a B, which stands for rate. And instead of T for time, they're using X. No big deal. There are a lot of different forms of PERT equation using different variables. There's this AE to the BX. There's, let's see, what's another common one? NE to the KT. It's the same thing, okay? This number out in front of E, that's always your starting amount of whatever it is we're measuring. This is always the Y, this is always your ending amount. E is a constant, 2.7-ish, know it. R is just your rate, and T is time. Or in this case, A is your starting amount, B is your rate, X is your time. Not a big deal. And if your rate, if B or R, whatever you want to call it, if your rate is positive, if you have a positive rate, whatever it is we're measuring, the amounts we're measuring, they're growing. The amount is increasing. But when your rate, R or B or whatever you want to call it, is negative, when you have a negative rate, then it's a decay model. So whatever it is we're measuring, the amount of it's decreasing. The amount is decreasing. Okay, so there you go. Let's get started. For the first problem, we're starting with the logistic growth model, which is one of those ones that I said you don't have to be able to build the equation. See, they've already got it there for you. You just have to know how to plug numbers in. So, I've kind of highlighted some stuff for you. F stands for number of people who have become ill. T is time in weeks. Question, how many people were ill? Oh, hey, we just talked about that. That's F of T. So this right here is telling me to find F of T when t is 4. So you can see that I rewrote the formula. Instead of f of t, we're now calling it f of 4 because 4 is what I'm plugging in. Same. Plug in 4 for t. Type it in your calculator. Again, you're going to need parentheses around your denominator. And then your calculator is going to tell you, I got 1,080.2 people. I know you can't have 0.2 of a people, but I just follow the directions. It's what the directions told me to do. All right. Feel free to pause the video and write and catch up. The next one, let's see. All right. The next one, oh, lucky you. You are given an equation, and it's a PERT equation. Y equals P e to the RT. And it says the population is represented with Y, so I'm going to make that this kind of orangey color. X is my years, but it's my years since 1980. And in how many years, that's telling us to find X, will Y be 2.5 million? Well, be careful when you're putting 2.5 million in. You don't have to put 250000000 because this is in millions also. So we're just going to use 1.8 and 2.5. Okay, so you can see in my next line, I subbed in what they told me. I'm trying to find X, and I subbed in 2.5 for Y. Now, according to what I showed you a couple of days ago, I need you to isolate this exponential expression. So look at where your X is. X is in your exponent. Make sure you're only looking at the base and your exponent, which means the 1.8 needs to go away. So divide both sides by 1.8. In order to get this out of the exponent, remember you need a log in front of this, and then we can bring it down. So you're going to keep it legal, you're going to log, natural log, both sides. I natural logged both sides. I brought my exponent down in front. See, this used to be my exponent. And don't forget, natural log of e is just 1, so that leaves me with simply 0.026x. And then I'm going to divide by this. And I get approximately 12.6 years. Moving on. See if I can fit all that in there. All right, this one's kind of cool. This one did not give me an equation to start with, so we're going to build our own equation. So we have a starting amount of 50,000 people in the year 1950. But 50 years later, so T is 50, 50 years later, the population now had dropped to 20,000. So starting amount is 50,000. Ending amount, after 50 years, our ending amount was 20,000. Determine a formula. Okay, so here's what it's saying. Determine an equation that has an x in it and a y in it. Just like this one. So we need P, we need R, and our formula has to have an x in it and a y in it. So that's our goal, is to determine that formula. So the first thing I did is I plugged in everything I know. I plugged in starting amount. I plugged in ending amount. I plugged in 50 years. Now, look at this. The only variable in the whole problem, the only variable, remember that's not a variable, the only variable is R. You can totally solve for R. So we're going to isolate this expression, so I divided both sides by 50,000. We want to get this out of the exponent, so I took the natural log of both sides. Oh, and I reduced. That was silly. I reduced. I'm going to bring my exponent down to the front, and I brought down the 50r, and remember, it's 50r ln e. Well, ln e is just 1. And to solve for r, I'm going to divide by 50. Divided by 50. I got r. Look, r happened to be negative. Does that make sense? It should. This is a decay problem. We're going from 50,000 people down to 20,000 people, so the amount of people is decreasing. So it makes total sense that this is going to be a negative rate. Okay, so then here's what our formula looks like. Don't put the ending amount in. We want to leave this open. Don't put the time in. We want to leave this open. So once we have our starting amount's not going to change. So this is the amount of people we started with. Now we know our rate. And now, if somebody comes along and says, hey, I see you started at 50,000. How many people were there at the end of 10 years? You'd be like, hold on a minute. I'll plug in 10 and tell you. So this is like the formula that it's asking for in the problem. All right, and then we have a cool banking question. We have two parts here. We have a part A and a part B. So we'll focus on part A first. We've got $600 was invested, and I'm color coding that green. That's going to be our starting amount. That's P. Compounded continuously. Use the part one, not the 1 plus whatever. 3205, that's our ending amount after 10 years. So T is 10. Find the interest rate. So first thing we got to do, part A, find the interest rate. So you can see how I plugged all of our information in. I put my starting amount here. I put my ending amount here. And starting amount, ending amount, remember those two numbers were after 10 years happened. So this 10 years goes with this starting amount and this ending amount. And we're going to solve for r. It's the only variable in our equation. Okay, do what we've been doing. Isolate this. Get rid of the 600. This needs to come out of the exponent, so you need to natural log both sides. When you bring this down to the front, ln e is going to be 1. So there you go. And I'm going to divide both sides by 10. And then here's what I get. As a decimal, the rate is 0.167 something, something, something. That number should be on your calculator right now. Store it. I think I've shown you how to store things on your calculator. If I haven't, be sure and ask me in class how to store it. So store that in your calculator. This is our rate as a decimal. This is our rate as a percent. So if somebody were talking to us about, hey, what's the interest rate? You would say verbally 16.7%. Which, by the way, 16.7% like never happens. That is an outrageously high interest rate, but whatever. When you're talking about it, you talk about it as a percent, 16.7%. When you are doing math on paper, the number that you write on your paper is the decimal version, 0.167. All right, so using those, let's go to part B. How long did it take to double the investment? So keep in mind, our initial investment was $600. It's asking how long did it take, so I'm going to find T. So T goes there. I now know my interest rate. Starting amount, interest rate, this is what I'm trying to find. I need a number over here, and you're going to come up with it. Think about this. How long did it take for our initial investment, $600, to double? I think you want to make that $1,200. Right? That would make it double. Original, ending amount. All right, so $1,200. Now, you're solving for T. T is in your exponent. Get rid of the 600. 1,200 divided by 600 is 2. Look where T is. We're going to natural log both sides. Move your exponent down to the front. Divide by 0.167. Oh, hold on. Don't just divide by 0.167. Divide by that stored value in your calculator. So if you store it as variable A, then you need to do ln2 divided by A. Whatever you called it on your calculator, that's what I want you to divide by. And you get approximately 4.1 years. It took about 4.1 years for our investment to double. Now I want to point something out to you. This is really cool. It took 4.1 years for our investment to double. What if I had invested more? Do you think it would take longer to double or less time to double? Let's say I invested, instead of $600, let's say I invested $2,000. $2,000. Do you think it took longer than 4.1 years or less than 4.1 years to double? Or the same amount of time? Well, let's kind of figure it out. Won't do any math. I'll put my pencil down. Let's say this was 2,000. What would this be? Good job. 4,000. 2,000. 4,000. What's the first thing you're going to do to find out how many years? You're going to divide by 2,000. What's 4,000 divided by 2,000? Oh my gosh, our problem becomes exactly the same, which means our answer turns out to be exactly the same. So at this rate, it doesn't matter how much money you put in the bank. If that's your rate, it's going to take that long for the amount to double. That's kind of cool. You're kind of like, huh, didn't know that. Moving on, example 5. Example 5 is one of those kind of complicated ones. It's a logarithmic formula, and all you have to do is know how to plug in numbers. So watch what I'm doing. Oh, by the way, there was a typo here. This is supposed to be f of x equals, and I don't think it says that on your paper. So make sure it says that, will you? F of x equals. Sound levels measured in decimals, measured in decibels, is f of x. X, right here, is the intensity of the sound measured in watts per square centimeter. Find the decibel equivalent, so this matches this. Find f of x when the watts per whatever centimeter is 10 to the negative 2. So 10 to the negative 2 is going to be subbed in right there. That's all you got to do. So when you're writing it on your paper, say, hey, I'm subbing in 10 to the negative 2, and then sub in 10 to the negative 2. Pick up your calculator and type that in and hit equals. And I got 140 decibels. All right, number 6. Again, I'm color coding it for you. I'm trying to make this as simple as possible. It's telling us this is the equation that we're going to use. Not sure what happened, but I think I'm still recording. So it's telling us this is the equation we're going to use, not PERT this time. This is the one we're going to use. How long would it take, find T, to double your money, however much you invested. However much you invested, we want it to double. This is your interest rate. It's compounded quarterly, which means N is 4. That's part A. So, ready? For part A, let's start building our equation. Part A, it said my interest rate is 12%. I put that there as a decimal. Compounded quarterly, N is 4, N is 4. Find T. Now it's up to you to come up with a starting amount and an ending amount. Did it tell us how much we started with? No. It just said how long would it take to double your investment? So you come up with your own investment. What do you want to invest? Anything. If you're going to put money in a bank, how much money could you put in a bank right now? Maybe $100? Let's go with $100. What if your investment was $100? Now, you're a teenager. My investment might be a little bit more than that, but here's the cool thing. It doesn't matter. Because if you invest $100, when it doubles, how much will you have then? You'll have $200. If I invested more, I would end up with more. But what the cool thing is once you divide both sides by 100, you're going to get 2. I'm going to get 2. This number is always twice what this number is. So it doesn't matter what the numbers are. When you divide them, you're going to end up with a 2 over here. All right, so then I divided, that's a 2. I did this on my calculator. I did 1 plus this divided by this, and I got 1.03. It was a nice decimal. I wrote it. Look where your variable is. Your variable is in your exponent, and you need to get it out. You need a logarithm right here. So I put a logarithm right there. Did it on both sides. I'm going to bring my exponents down to the front. I'm solving for T. What's going on right now? T is being multiplied by 4. It's also being multiplied by whatever number this is. I don't know what this is. I don't care what it is, but it's just a number. So let's divide by the 4 and that number. Let's divide by the 4 and the ln 1.03. Let's divide by the 4 and the ln 1.03. Careful, use parentheses. And I solved for T and I got 17.4 years. Now, the next part of the question, it's not worded well. It's kind of ambiguous. So I'm not going to work it out or anything, but it's basically saying if you do the same amount of time, and the same rate, how much do you need to put in to end up with 500,000? And it's kind of a trick question. You would have to put in 250,000 in order for it to double to be 500,000. Okay, let's get to the exponential growth problem. Exponential decay. All right, so we're doing half-lives. A half-life, think biology, is if you are working in like a petri dish and there's a substance in a petri dish that's going to like eat away at itself. And so you put the substance in a petri dish, you put it in the window, and you leave it for a couple of weeks, and you come back, and now there's less of it there. It's like eating away at itself. That is, that's exponential decay. And half-life is however much you started with, how long did it take for it to eat half of itself away? How long did you have to walk away until you could come back and there's only half of it left. That's what a half-life is. So, example, if you have 100 grams of a substance and the half-life is 15 years, it's a long time, then after 15 years pass, you won't have 100 anymore, you're only going to have 50. That's what half-life is. And then if you have 50, if another 15 years pass, then you're going to have half of 50, which is 25. So, here we go. It's talking about this radioisotope, and this is just its name. Do not let this freak you out. In fact, I shortened it. I'm going to call it Ray. Ray, this radioactive isotope, Ray has a half-life of 1,620 years. Holy moly. That means if we started with 100 grams of it, then it would take 1,620 years to reduce itself to 50 grams of it. So that's how long its half-life is. So if the original amount was 5, if P was 5, how much would remain? Find the ending amount after, 10,000 years passed. So when T is 10,000. Now, watch what happens if I try to plug in stuff from the problem. So if I try to plug in original amount, I put a 5 right there. And I plug in 10,000, I've got 10,000 right there. Find the ending amount. Okay, slight problem with that. I have two variables. That's a variable, that's not. That's a variable, and that's a variable I can't solve for anything. So this is not a good way to start this equation. Here's what we're going to do. Here's going to be our plan. We're going to find R first. We're going to find the rate of decay for Ray. What's Ray's decay rate? And that's gonna hold true for this whole entire problem. Let's find R. So if I'm going to find R, I need numbers to plug in for a starting amount, an ending amount, and a time that passes. Look back up in the problem. Are there any numbers that they gave you that you can say, oh, yes, yes, yes. If the starting amount is this, then this much time passes and this is left? It doesn't say that anywhere. It doesn't give you a starting amount, a time, and an ending amount. So this is where you're going to have to use your brain. It does give you a half-life. What if I put in for T, hang on, I forgot what it was, 1,620. 1,620. What happens in 1,620 years? Well, however much you started with, after this many years, however much you started with, it's eaten away at itself, and there's only half of it left. You pick a starting amount. I don't care what you pick. Pick a starting amount. You know what? Let's not even pick a number in the problem. You pick your own starting amount, like 20? 20. What if we start with 20 grams? After this much time passes, how much is left? Yep. Now, look, here's your variable. Get rid of the 20. When you get rid of the 20, this is 1/2. It doesn't matter what we chose here. We could have chosen 50 and 25, and this is still going to be a half. That's the cool thing about it. Okay, so I got this. Let's get R out of here. I need a natural log both sides. Right? Natural log both sides. Bring the exponent down. divide by 1620. I got a negative number for r. Makes sense, it's a decay problem. Our amount is decreasing. We have a negative rate. Store this in your calculator. We're going to use it for the rest of the problem. Now, let's go back to part A. Part A, it gives us a starting amount. It gives us 10,000 years. We needed a rate to figure out this number. Plug it in your calculator. You got 5 times e to the, hold on, use your letter wherever you stored this, times 10,000. And your ending amount, I bet it's going to be less than 5.069 grams. Okay, and then part B. Part B says, how long would it take, find T. This is a little tricky. I'll get to this in a minute. We want 25% of the initial 5 grams. Okay, so we know that P is going to be 5. P is going to be 5. I have R. T is what we're finding. And our Y value, we want it to be 25%, 0.25 of the original amount. So I took, I don't know if you can see that. If I want 25% of it left, I took 0.25 times 5, the original amount. This is how much we want to be left, remaining. This is how much we want remaining. So, remaining or ending amount, beginning amount, rate in my calculator, find T. I'm going to divide both sides by 5. Natural log both sides. Bring my exponent down. Divide by that stored amount in your calculator, and you get 3,240 years. Okay, so I strongly encourage you to practice with these. You're going to have to be able to set some of them up, find R in order to continue for the rest of the problem. Practice, practice, practice. That's your best bet. Good luck.